So Penrose uses the Mandelbrot set to say, okay, this black area, this is non-computable. We can compute all this colored stuff, and so we can zoom in, you know, kind of narrow down where the black area is. So we have an algorithm for the colored stuff. We don't have an algorithm. We have no way to predict the black stuff, where it's unbound, or where it's bounded, because it would have to take an infinite number of iterations to be able to determine that. And so Penrose kind of just points to that and then moves on and goes into the quantum stuff and says, okay, but the quantum thing of superposition into collapse is how we're going to get our non-computational process, our timelessness into time, kind of it. But Notal takes the fractals further and says, okay, well, like I mentioned earlier, that, you know, a particle may move along a path, and it may look like it just moves in a nice smooth line, but if you zoom in on that line, it's no longer nice and smooth. He claims that space-time at the smallest dimensions is very irregular, to the point at which you can't determine the difference between two space-time paths, basically. So he says, between 2 points, you know, a particle is trying to get from here to here. And he says there are infinitely many geodesics, or the straightest space-time paths that it can take between those 2 points, because of the depth we just saw of the Mandelbrot set. It can have such, you know, tiny differences that there are infinitely many possibilities. Infinitely many possibilities for differences, therefore infinitely many possibilities for different paths. So a particle chooses only one of these paths, and this is where what we can know and what we cannot know comes in. If we measure it, we can know what path that particle takes. If we don't measure it, we don't know. And so that's the particle aspect of wave-particle duality, and Notal aligns the wave aspect with the properties of the family of geodesics. So all of these infinitely many paths have certain things in common, and that is encoded in the wave description of the particle. And so the wave description is no longer possessed just by one path. It's the whole potentiality of possible paths for that particle. And so in a sense, it's non-local. And it doesn't necessarily, you know, get collapsed or disappear when you measure a particle.
Loose down.
I have to plug it in. Sorry, guys. That might take a second. Okay. So the particle chooses one of those paths, and so he identifies the properties of a particle with that one path, and the property of the wave with all of the possible paths. So, like the boundary of the Mandelbrot set, these paths are infinitely intertwined, making it impossible to determine which path the particle chooses unless we take a measurement. And so that gives us our indeterminability, uncertainty, things like that. Okay, so the properties of this family. Okay, good. Dun, dun, dun. Okay, Penrose kind of ignores the fractal stuff. He does talk about it a little bit, but then he goes on and says, okay, it's the quantum processes of the brain that generate consciousness. Should I go into this, or skip it? Less time. What do y'all think about time? I think this might be. Yeah, I could go into this, or I could skip it.
Go into it.
Okay.
I have a question.
Yes.
That relates to this. But I mean, I'm not saying I'm going to ask right now, but
okay.
In other words, it'd be a way in which you could present some of these ideas.
Some of the the question and answer time.
Yeah.
Great. Okay. Good. We'll do that. We'll see if we can get Dawn back online here.